Okay, thank you very much, everybody, for attending this seminar in the context of the CRNS webinar series. It's a pleasure to me to introduce our colleague Aise. It's very difficult to pronounce her surname, so I will let her to pronounce it. She is assistant professor in computer science at the University of Nottingham, and before she was a senior lecturer at the University of Lincoln, and she was also a member of the Lincoln Center for Autonomous Systems. In the past, she also, had several collaborations with few colleagues of mine in my previous institutions at Sapienza University of Rome. Her main interests and research span across human-robot interactions, haptic interfaces, and assistive robotics. And it's a pleasure to me now to leave the floor to her and to her presentations about haptic communications and shared control of human-robot interactive systems. Thank you very much, Aisha.
Thank you, Mario. It's very nice to join this seminar series. So as Mario has introduced me, my name is Ayşe Küçük Yılmaz. It's a very hard surname. And as he has introduced, I'm an assistant professor in the School of Computer Science at the University of Nottingham. And today I am going to talk to you about a general overview of my research enabling haptic shared control systems while interfacing humans and robots. And I will start my talk with a little introduction of myself. So I started my robotics journey in 2007 when I was a PhD student at Koç University. And by then I was mainly working with haptic interfaces, which are these small robotic arms which allow you to feel forces that you can render on a typically virtual scene. And we were actually working on mostly simulated worlds, virtual worlds, and looking at how humans can interact with computer agents. In 2010, I have visited the Technical University of Munich, and that was my first interaction with real robots, where we integrated our mechanisms that we implemented for human-computer interaction on a real man-sized mobile robot. And the idea that we had during my PhD and in the Technical University of Munich was focused on the role distributions between two agents. So how should a robotic agent assist a person, not by only acting like a follower, but acting more like a proactive entity that is like a peer to the human. And during these studies, we had focused on understanding how we allocate these roles dynamically, how the human and the robot should exchange their control over the task by introducing haptic negotiation mechanisms, which look at the forces that are applied on a task and look at how they can be used to change the dominance behaviors of agents. In 2013, I moved to Imperial College London for my postdoctoral research. And in Imperial, I worked on an assistive wheelchair, and the project that I worked on was focusing again on shared control and how we can teach a robotic agent, which is the wheelchair in this case, to assist a person while the person is actually driving this robotic device. Afterwards, I actually moved to Turkey, and I worked as more like a teaching assistant professor in a Turkish university. And then in 2017, I moved back to the UK, and I started working in the University of Lincoln. And in Lincoln, we have worked with a few different robots. So one project that I was involved in was also focused on mobile robotics, and we had worked with this museum robot, which is called Lindsay, which is currently working as a tour guide in the Lincoln collection. And we had programmed certain behaviors for the robot to enable long-term autonomy by putting the human in the loop to save the robot when the robot needs it. And mostly my more recent work is focused on teleoperation. So I, at the moment, work only with robotic arms, and we use typically these Franca Amica arms to enable fluent teleoperation, where the human and robot autonomies are again shared to create this synergetic, maybe more symbiotic relation to enable very complex sorting or segregation kind of tasks, which typically find their applications in the interior robotics domain. So during my journey and my research, I have been initially working with robots that are only collaborating with humans, and then I moved to more learning methodologies. So I'm currently also focusing on robots that learn from humans, and the ultimate aim of my research is to enable robots to complement humans. So this can be a short summary of all my research interests. So unlike many people in the robotics domain, I don't really try to make these robots fully autonomous, but I try to make them work better with us. So I try to find ways to get the best of both worlds, get the powers of the human and the robot together to come up with better symbiotic structures. And as I say, the topics of my research can be summarized within using these keywords maybe. So I work on adaptive haptic shared control. So I try to come up with systems that implement shared control, and what this means I will explain in a moment. And I tend to rely on the haptic modality, which is about the sense of touch, or more about the forces that we use while interacting with within physical interaction. So I build haptic guidance mechanisms, I build dynamic role allocation mechanisms, and in doing so, I make use of machine learning and look at how we can learn skills for the human, or how we can understand interaction states while two agents, humans or robots, are interacting together. And as you know, many of robotics talks, I think, start very similarly. I will do the same, and I will talk about a contrast between the industrial robots and the robots that we have at the moment. So in the, let's say, industrial domain, in more old-fashioned robotics, if I may say, the purpose of robotics is typically automation. So we create robots to give them boring or repetitive jobs that people don't want to do, or we give them some jobs that are not really safe for the humans, so that we eliminate these risky or dangerous situations. And typically the industrial robots, or any robot that you see in a hazardous environment, are very big. They are really very strong and big robots that can work at very high speeds, but they are designed to work in typically isolation from humans. So you wouldn't typically see a human hanging around and changing the environment. And you don't really see the environment changing too much. So everything that the robot does is pretty much hard-coded. And because nothing really changes, that hard coding doesn't really cause any problems while the robot is performing its task. And because of this, you don't really need to have maybe very complex sensory capabilities, just as we have it with the robots that we have in more futuristic scenarios. So today's robots, I want to maybe imagine a little bit with you, are designed, or we try to design them to work along with people. Because when developing today's robots, we try to come up with these robots that can maybe physically collaborate with humans, and this can be maybe autonomous cars which can work with you to improve your driving, so that you don't really get into a crash, or you don't actually have to get tired while driving. Or it can be more like cobots or mobile manipulators which can carry stuff with you. They can be even those robots which could enable you to go to a museum while you're under lockdown, so that you can get onto remotely on the robot and go around the museum while driving around with other robots maybe, or other people. And physical rehabilitation or assistive robotics is another area that today's robots focus on, so that we physically bond the robot onto a human. So there is a very, very strong coupling with the human and the robot. And there are these robots which enable social interaction, such as social assistive robotics or robotics for mental health. And these kind of robots are probably harder to implement, because they do need to interact effectively with the humans. And this cartoon basically shows like this Hollywood-inspired expectation from our robots, which looks like a human and can very effectively talk to you. And possibly these kind of robots would come up with their own mechanisms of interacting with you, but still able to deliver the task that you're interested in. And from this discussion, I want to actually tell you my opinion, or some group of people's opinion, about full autonomy. So when we think about these robots who have their autonomy and who can complete these tasks, some researchers actually think that achieving that full autonomy in unconstrained environments is not anything more than a myth. Because if you have ever worked with robots, or if you have tried to implement robots in a slightly realistic scenario even, you can see that it is really very hard to get them operate under full autonomy successfully. And in such cases, you still rely on human intervention or human decision-making capabilities. For example, if you're in a situation where you have this robot to sort maybe dangerous materials in a nuclear reactor, you could want a human to maybe point to you what should be placed in which place, or what is dangerous or what is not. And these kind of decisions are actually very hard for the robots to do, whereas it is easier for us. However, the robots are much more precise, they are much faster. So they have their strengths and we have our strengths. And this is the core of all my research. And thinking about this core of my research, I want to discuss about this concept of levels of autonomy. So this is more prominent with the coming of the autonomous cars. So they have defined actually these 5 different levels of autonomy, which is ranging from teleoperation to full autonomy. And actually this spectrum of the levels of autonomy is consistent across all robotic applications. So at one end of the autonomy spectrum, there's teleoperation, which is something like a Wizard of Oz simulation of a robotic operation, where you manually teleoperate a robot. So the robot is merely a tool that you move, something like a master-slave system, which doesn't have any kind of intelligence in it. And then if you move a little bit towards autonomy, you could have maybe scripted robot behavior. So you could have some smaller segments or primitive motions that you can implement, or maybe some waypoints that you give to the robot under constrained scenarios. And the operator can maybe run these pre-scripted behaviors while operating the robot. And this could be something like a small humanoid robot interacting with a person, and the operator maybe selecting these pre-scripted behaviors of reaching or maybe looking at some location to mimic some kind of intelligence in the robot. There is partial autonomy, and partial autonomy is a hybrid of autonomous and a human control system. So I tend to call this traded autonomy typically, because in partial autonomy, there are aspects that the human can actually autonomously complete, and there are aspects that the human still needs to intervene. So it is at some moments the human is performing the task, and whenever it can, the robot is taking over the control and fully completing the task. Then there is supervised autonomy, and supervised autonomy is similar to partial autonomy, but in this supervised autonomy, you tend to go toward a little bit more of a fully autonomous robot, where the system can actually act autonomously most of the time, but there's a supervisor. And in case of dangerous situations or in case of decision points, the humans can still take over the control of the task. And obviously, there is the full autonomy at the end of the spectrum, where the robot does not need any human intervention and can operate fully without humans, which is typically the myth that I am talking about. And in between this teleoperation and autonomous operation, there are all kinds of these behaviors, which I will call human in the loop, because in all these behaviors, you have to have a person somehow interacting with the system. However, in all these scenarios, what you can see is you have this turn taking between the human and the robot. So the human tells the robot to do something and the robot performs something. And this is one way to implement the human in the loop. And we need human in the loop because automation is by definition problematic, and it has been discussed for decades now. And there, for example, Bainbridge has indicated that as the tasks get more complex, as long as you demand this more complex control behaviors from a robot, the more that you need help from a human operator. And in Norman's problem of automation, feedback, and interaction, what he states is that you need to implement appropriate interactive systems by always assuming the existence of errors, by enabling some kind of feedback continually, and continually interact with operators in an effective manner. And probably a quote from Murphy should have been included here, saying, if you anticipate something bad to happen, it will happen when you're working with humans. Because these scenarios that we are talking about typically are very complex because the environment gets complex, because task definitions change and so on. And because you can't really program autonomous behaviors for such things, you start putting a human in the loop, and that also starts introducing extra and extra problems in your life. Because we have human errors, so the human that is involved in the task could be the designer, so the autonomy by itself can be problematic. It can be the operator who's maybe manipulating the robotic system to support it. Maybe he is in error, maybe the decision making contains errors and so on. So something else that is lacking in this framework is feedback. So you have to also kind of provide feedback from the robotic system to the human, so in a continuous way, in a way that does not annoy the human or does not cause overload on the human. And in order to enable all these things, we need a system which is adaptive, which is compliant, instead of having a rigid, completely formal, autonomous mechanism. And as I indicated, the current solution to human in the loop, by using the human as an emergency system that needs to be aware of the system state or system failures or system capabilities all the time, is very, very demanding for the human. And if you have a human that has the sole authority of switching the control authority, that is on itself problematic, because the human needs to be alert at all times. And in case of very dangerous tasks, in case the human does not really perceive a dangerous situation, the results could be catastrophic. And I want to give an example of a traded control scenario we have implemented to show you a typical human in the loop scenario. So in these two videos, what you see is our robot Linda working in our lab. And we have actually used the ROS move base to implement some autonomous behavior for the robot. And anyone who has worked with mobile robots possibly have encountered similar situations where you design an environment, you change something slightly, or you set some of the parameters of the navigation, and it doesn't really work correctly in all situations. So in here, for example, there are two situations we show. In the first one, Linda gets stuck on a corridor, even if it can actually pass through it. And in here, there is a node which is overlapping with an obstacle in the topological map, so it can't find the correct route. And all these situations actually are very simple situations to solve for the human. And in here, we implement this traded control mechanism so that we have the global navigation, autonomous control of the robot, and we enable a human to step in, and in case the robot fails, in case the robot can understand that it fails, he could show some routes for the robot to recover from the error situation. So what we implemented here is a two-layer learning framework where we have a failure classifier. So we implemented a Gaussian process classifier to look at the laser scans of the robot, and the robot actually classifies the error in a certain situation, and then it asks the human to show it how to recover from that problem situation. And these recoveries are also implemented as Gaussian processes. So we execute a recovery trajectory, we model it using Gaussian processes, and we feed into the robot's library as a local navigation strategies, so that the robot knows that in case of this kind of a failure, I could actually step in and use that local strategy to get out of it. And this is what we came up with in the end. So the robot is actually moved by MoveBase, and it faces a failure, and the human steps in, and the human basically just shows this is a safe thing, so you can just move on, and the robot learns it. And in the next time, for example, we have this behavior in the library, the robot encounters something similar, and it asks the human, should I proceed with whatever I have learned? And if the human approves that, the robot actually applies that trajectory behavior. And this is a solution to enable long-term autonomy, but it does require this interaction with the human. So there is the asking question, and there is maybe the taking fully over control phases, which makes the operation a little bit not fluent. And the applications that we are thinking about are those that we try to make really very much fluent. So there is this horse metaphor we typically use in haptic shared control when we imagine that the ideal robot that we want to build is very similar to the robot. So using these reins, you can actually signal what you want to do with the robot, but the robot has already some autonomy, and it can take decisions on the fly. And you don't actually take over the control fully, because both agents have a certain amount of control at all times during the system. So whenever I talk about shared control, I actually talk about this system where the human and the robot share the control in varying degrees at all times. So it's not a trading of the control scheme. So the robot in such scenarios is aware of the environment, is aware of the intentions of the human, and the aim of the robot is typically to achieve better performance or safety through symbiotic actions. And in haptic shared control, we make use of this channel of haptics to communicate intentions, so that the human can have some kind of feedback about what the robot is doing. But these intentions of the robot, in many of the scenarios that I will show you, can be easily overruled. And haptic shared control enables us, or in the examples that I will show you, will enable us to dynamically change the control authority through forces. And I will show you some examples where haptic shared control is used to make the robot adaptive to human operation, but using variable degrees of autonomy. So it's not like the robot has the full control or the human has the full control, and basically it's a on and off case. And using haptics, we try to add better awareness of the system state and decisions. And in all of the examples I will show you today, I assume that humans will always have the decision power. So they will always have the autonomy to overrule the system decisions. And this is one of the first examples that I had worked on. And this was a virtual world example where we devised this board game to study this haptic negotiation idea. So the idea that we had here is, if we had this task which has clear regions where we have really a lot of difficulty, for example, what is asked in this task is to go to these target locations, but the targets are placed in between very narrow tunnels. And it is very hard for the human to be very, very precise. And in this task, we assume that the human could get help from the robot if he has difficulty. And this task was designed with the assumption that it would allow us to maybe observe some kind of role exchanges. And eventually it did. In here, we didn't really implement too much intelligence in the robot. We basically implemented a finite state machine where we had the human control and the computer control at the extremes. And looking at the forces that the human is applying on the system, we were transitioning between human control and the computer control. And in the end, we showed that by changing the control levels, the autonomy levels of the human and the controller, the robot, we achieve much better performance in terms of time, in terms of energy, in completing the task when compared to manual operation or when compared to equal control of the human and robot autonomies. And afterwards, we moved on to a real robot example. And in here, the task is almost the same. So what we are doing along with the robot is we are trying to move this table into 4 configurations in a complex scene. So the task is more challenging here because it does require 2 actors to collaborate. The table is very bulky, so you can't really maneuver it using a single agent. And in here, the robot is haptically linked to the human. So there is a force sensor here where the robot can actually read the forces applied to the table by the human. And what we had implemented here was a really symbiotic relationship. So we assumed that each agent are actually really peers. So each agent has the inverse model of the table. Each agent has this impedance control in the models. And using those, it can come up with certain wrenches that should be applied on the table to move it, which consists of the plan of the agent. And these are then negotiated through an effort role behavior to assign control levels, autonomy levels to the human and the robot to collaboratively move this table. And we did this by integrating a role behavior negotiation block into the control scheme so that we look at the forces that are applied by the human and the robot, and we create this role allocation setting, and we assign the autonomy to the human and the robot appropriately so that they work more effectively. And what these 2 studies showed us was that in both studies, this dynamic role allocation behaviors were shown to improve task performance and effort requirements of the humans. And also, we showed that the haptics, the use of haptics, the use of these forces can on its own allow the robot to infer the intent of the human, so that you don't really need to look at the motion, you don't really need to have cameras to understand the intentions, but by only looking at the forces, you can try to understand the motion intentions of the human. And using that information, the robot can change its behavior and adapt better to the needs of the human. However, especially in the real robot experiment, what we observed was humans still favored constant role allocation because this very proactive behavior felt very intimidating to them. And that kind of hints onto some further research onto this to study what is the best way to interact with the human. How can the robot make it clear that the decisions or actions are actually for the favor of the human. So on a very similar thread, I have worked in assistive robotics, and the shared control idea applied on assistive robotics is an interesting one, because in here you tend to move toward building more personalized systems. And these videos, I will show some videos here, actually illustrate the assistive robotics application. So we were working on this wheelchair, and in here Tom, who's in UCL right now, is demonstrating a fully autonomous robot, which we thought as an engineering perspective was a very nice solution. However, the real users actually hated this solution, because especially wheelchair users really want to be on control. They don't want to be carried around. And on the other end of the wheelchair user spectrum, we have different kinds of users. For example, this child has a surgery, and because of the surgery, he had lost his sense of fear. So the NHS wouldn't really give him a robotic wheelchair because he was dangerous to the environment, to himself, and so on. And as a very small child, because he couldn't really move on his own, his option to cognitively develop was very, very limited. And in such a user scenario, what you should actually ensure is the safety. And this kind of different personalities, this kind of different personal choices or personal needs is an open invitation for building shared control systems. And the system we developed here is, again, a haptic shared control system, which is like a prototype system, obviously, not to be given to this child. But what we have here is we can allow a person, for example, or an autonomous agent to move the wheelchair, but we can also make the human at all times be capable of controlling or taking over the control of the wheelchair. And in here, initially, what you see is the robot is controlled by a remote teleoperator. However, if I feel maybe threatened, or if I feel that the autonomy is not doing something correctly, or the remote operator is not something doing correctly, I can hold the joystick and I can stop or move the wheelchair in the way that I want to. And what we have implemented here is actually another regression problem. So we found that a learning from demonstration approach to teach a robot good assistance policies was a nice approach in this wheelchair scenario. So what we did was we haptically linked two agents. So in here, in a demonstration trial, the remote human is actually looking at how the human is driving around. And depending on what the human is doing, for example, he was correcting the motion here because I was driving very close to the obstacle. He's providing some assistance. And what we do after this demonstration is taken is we look at some data from the human, from the user, from the environment, from the robot, and we train a Gaussian process regression model to learn the corresponding assistance commands. And when the remote teleoperator is gone, when I'm alone and driving, the assistance is always on. And what it does is it tries to mimic what this remote operator is doing. And in here, there are these two lines. One is my commands, and the yellow-green one is the assistance commands. And in here, it's clearly shown that the assistance is trying to turn around these corners a little bit faster than me, so that I don't really get very close to hitting any of the corners. And what we had also shown here is the system was actually learning and really mimicking the behavior of the robot, of the remote person. However, if I take a different path than what the system was demonstrated on, for example, all the demonstrations was in this route, and if I choose to maybe move forwards, the model does allow the user to explore different trajectories, because in here, the green line pulls me toward the open area rather than moving me to the corridor. because my intention, my haptic intention, is clearly in the direction of the open area. And using these kind of learning methodologies, you can also learn or incorporate certain policies to be applied as the assistance while you're still negotiating over haptics to change autonomy behaviors. And we have now seen certain roles for the robots. We have seen robots working as a partner, a learning partner, even robots working as an assistant, or robots working as a team member, such as someone who carries some heavy load with you. But there are also different roles for the robot. The robot can be your teacher, the robot can be your therapist, so that the task of the robot can be not strictly collaborative. And we have been doing some work around learning from human-human interactions. So we have been working on this for a few years right now, and we had done multiple human-human interaction studies where we collected data and we published the raw data as well, if anyone is interested. And what we are currently doing is we are actually mining this human-human interaction data to understand important stuff that the humans are doing, especially during their motion, how they are interacting, how they are facing maybe conflicts in motion, and how they are resolving these kind of things. And up to now, we have implemented certain mechanisms to do automatic recognition of skills, automatic recognition of conflicts, interaction states, and we can do it in real time. And we are at the moment looking at how we can learn controllers to define different interaction behaviors so that we can make a robot competitive as well, to maybe make it work like a rehabilitation robot. And we are also implementing certain adaptive shared control formalisms and non-verbal communication formalisms on top of this to move this understanding onto human-robot systems. So to conclude my talk, I will show you some of the stuff that we are currently doing. So in the last 2 years, I've been working with robotic arms, and in Lincoln, as part of the NCNR project, we have developed this teleoperation system. So we have different ways to teleoperate robots. So we have direct view teleoperation, where a person can manipulate one Franca arm to move the other one. And we have this configurable space so that we can put the human far away from the manipulated slave arm, so that we can have a more realistic teleoperation scenario. And we do have a system to enable bi-manual teleoperation, so that we have 2 masters controlling 2 slaves as well. And the systems have been demonstrated under long distance teleoperation. So this was an older demonstration where the teleoperation system was used to teleoperate a robot in our lab from an event in London. And currently we have done a lot of work on developing software interfaces, especially with the coming of COVID. We started relying a lot on simulation. So we have a full-scale simulation framework for the pandas, integrating PyBullet and Mujoko. And this is part of this HEAP project, which I'm currently leading, which is focused on benchmarking robotic heap sorting. So we are really relying on this simulation framework to look at how we can implement different algorithms, how we can benchmark these to advance the manipulation literature in robotics. And apart from the identical slave arms, we have integrated different hardware interfaces. We can move or interact with the simulated and the real robots using haptic devices and a simple maybe Xbox controller interface. We have different visualization interfaces showing different camera views of the robot and the environment, and we can one of our colleagues has developed this soft grippers, Khaled Al-Ganaidi from Lincoln, and we are using his grippers to complete our manipulation tasks as well. Okay. And one of the most recent work we have completed is the master-slave teleoperation over the internet. So we have integrated the teleoperation system using a haptic device. And in here, what we use is we use a WireGuard VPN to make the haptic device teleoperate the Franca arm from Nottingham to Lincoln using very, very simple filters and using ROS. And what we have seen here is we are able to really mimic the end effector position almost precisely and effector orientation very, very well. And the major difficulty we have is not on the haptic thread, but mostly on the video link where the human needs to actually see what is going on in the scene. And in a recent study, we had also worked on implementing virtual and real forces. So we are trying to also improve our teleoperation setup so that when we are using a identical Franca-Franca teleoperation setup, we want to feel these environmental forces, but also integrate maybe guidance forces. And this study led by Jayant was working on an architecture to integrate guidance forces with real forces using a two-layer force feedback architecture. And finally, this was Kim Tien Lai's master's thesis. We have implemented a shared control mechanism to guide the human to sort objects in a heap. And in here, what we saw is what we see is the robot trying to grasp certain objects in the scene, and the objects are actually colored. So it is the human who knows which object needs to go into which box. And based on the distance to the objects, we learn a DQuian model for human intent detection, and based on a reward based on the distances, the robot chooses which object it should approach to. And these approaching trajectories are learned through demonstration. So the robot has a library of behaviors where it chooses from within its library to approach and bin these objects. And in here, I think there is a short demonstration in the end. Okay, this is not here. But basically what we have observed here is when compared with a manual operation, this kind of switching behaviors by integrating the intent of the human and by looking at these learned behaviors to complement the human operation drastically improves grasping performance. So the number of grasping attempts significantly drops with this intent-aware haptic guidance paradigm. And that's all right now. And I will advertise a little bit using this opportunity. We will be hiring some new postdocs and some PhD students very soon in the coming year in January. And if you're interested in robot learning, role allocations, and shared control, you may contact me. And that's all. Any questions?
Thank you very much, Lise, for your presentations. Really very interesting. Any questions from the participants? Okay. I have an initial questions. Okay. What kind of methods or approaches did you use or did you apply to mitigate the main problems related to noise by using haptic device in robot control?
Yeah, so we are basically using a very simple low pass filter. So we are just interpolating the forces so that you don't really see these jumps when you're feeding back to the haptic device, and all the computation is actually done on a single computer. So what we are actually transmitting is only the displacements of the haptic device, and all the force computations are done on a single computer so that you don't actually feed back two different values. But having said that, what we are dealing with does not really support huge delays. So we are typically focused mostly on small delays and within the lab. And I think this different control architectures can easily be integrated if you have really stronger delays, like the 4-channel architecture could be possibly solve the problem.
I see. I have another question actually. What kind of problems did you find in solving the, let's say, the shared control, the negotiation between the human interventions and the robot actions, basically? Did you probably I didn't get it precisely. Did you use any model-free approach for managing the human interventions, or is there a sort of mixed initiative planning in place?
So the way that we implement the role changes, or how we change the autonomy from human to robot, is done in different ways, but in using typically a finite state machine. So in all of the works, we build these finite state machines and we change the criteria to trigger the state changes. So in the initial study, I actually showed the slide where we relied on the force magnitude. And for example, in the current work that we are working on, we are actually looking at these intentions, for example, and looking at, for example, the confidence of the intentions or confidence of the task to change the autonomy. So one of my postdocs is working on looking at task characteristics, for example. So looking at how consistently the person is doing the task is deciding on the confidence of the autonomy. So if the human has a lot of variability, for example, we kind of relax the autonomy on the side of the robot. And that is done through this haptic negotiation framework, which I had written back in 2010, which kind of is a way to weight the control commands as in a PD control. So what we are basically doing is we frame the whole architecture, this whole arbitration block as a joint PD control, so that by changing the stiffness of the controllers for each actor, we are able to make them more compliant or make them more stiff, which means for us a stiffer actor is actually more dominant. Does make sense?
No, yes. Yes.
Hello. I
Hello.
have a question actually. First of all, I would like to thank you very much about this very nice presentation. It was really inspiring. In fact, I would like to join this presentation a lot because I'm from Turkey and I got to know your name like 5 years ago from one of our co-advisors. So it was really impressive when Çağdaş Hoca mentioned about what you have done in there.
Okay.
And in fact, maybe I have to mention in here, it was quite inspiring for me. I'm doing my PhD in Norway right now in human motion estimation for human-robot collaboration. So it was quite inspiring for that too. So actually my focus is not really into haptics, but I was really impressed when there was one example you have showed with Phantom Omni controlling the Franca Amica robot. And currently I'm working on the mismatch with the human motions that actually human joints and the commercially available robots, the joints that they have, this really perfect circular motions that they have. So I was working on that. I'm working on that too. So I was wondering what kind of a control scheme, like task mapping maybe, what kind of a controlling algorithm do you use in the sending the commands from the Phantom Omni in the project that you mentioned to like the end effector motion control or like joint control? What kind of a procedure you follow?
Yeah, so for the haptic device, because of the nature of the haptic device, we are actually only controlling the end effector position. So we are not actually looking at the joint mismatch because basically the devices are quite different than each other. But this work I had shown here actually looked at how we can implement force feedback on a Franca arm. So this work here, maybe you can take a look into that, looks at two different ways to match the joints or match the feedback coming from the environment and render it on the master arm so that I can feel what the slave robot is touching. And we have tried mapping the end effector for torques and then using the Jacobian to compute each of the joints. And then because we are using identical devices, we also looked at all the joint torques because Francas also have joint torque sensors at each joint. So it was easy. And obviously,
my question is actually one previous project. If you go one slide back, you are using Phantom Omni. Was it there? Yeah, the Phantom Omni to control the I don't know if the end effector or the force torque
end effector
features. Okay, it was an end effector. So you are sending the position commands from the. Okay. Okay. That's
yes.
important for me because it's quite difficult to have the mirrored motion or like the shared control in the human joints with the robot manipulators. I really would like to look into that project.
Yes. So typically with the haptic devices, you only send the positions because that is the information that you have from those devices.
Okay. But can you also provide the torque information to the robot like this, they spread out the joints, or it's not something implemented here maybe?
So this device doesn't have torque sensing. So that information is not readily available. You can, but with the haptic device, what you're trying to do is basically to compute a torque and put it on the robot, render it on the haptic device so that you can feel it. So it's the nature of the interaction. It's not typically done in the other way around, where you read torques from the haptic device and send it to the other one.
Okay, I see. Oh, thank you very much.
No worries, thank you. Thanks for introducing yourself as well.
Okay, any other questions? So, Aisa, thank you very much for this presentation, and thank you very much also for supporting this series of events. It has been a pleasure to have your talk, and
it's my pleasure. Thank you for calling me. It was very fun. Hopefully it was useful as well.
Very useful, actually. Thank you very much.
Thank you. Hope to talk very soon.
I hope to see you soon. Okay.
Yes.
Bye-bye. Bye.